So the actual theory is pretty simple. This is everything you need to know to analyze moist air. And you remember there were 5 equations previously to convert between mass analysis and molar analysis. If you know both of them, you can solve any problems about this moist air. However, each problem is case by case, so you need to solve as many problems as you can to get used to, the dealing with these problems, okay? So the first problem, we have air enters a compressor. So we have a compressor like this. Providing power, W in power, it is that, so we add that on top of it. So this is the inlet, let's say number 1, and at number 1, pressure P1 is 50 degrees Celsius. I'm sorry, that is temperature. 0.9 bar. Temperature T1 is 50 degrees Celsius, and phi 1, which is the relative humidity, 70%. And the volumetric flow rate, V dot at number 1 is going to be 0.8 cubic meters per second. This is the volumetric flow rate at number 1. So there's no conservation of volume principle. So the volume flow rate at number 2 may not be 0.8 cubic meters per second. If you want to, consider conservation principle, you need to calculate the mass flow rate at number 1. That is going to be the same as the mass flow rate at number 2. Volume is not conserved. What about at the exit? We have temperature T2, 195 degrees Celsius. P2, pressure is 1.5 bar. And we assume that the compressor is well insulated. We want to determine the relative humidity at the exit, which is phi number 2. So how can we solve this problem? We need to calculate the relative humidity. We know the relative humidity at number 1. So from this, we can actually calculate the mass of water vapor at number 1. So let's do that. To use this relative humidity in our equation, we need to, calculate humidity ratio omega. Humidity ratio omega is 0.622 PV1 over P1 minus PV1. And in this equation, we do not know PV, so we are going to calculate PV from the relative humidity. This relative humidity, phi 1, can be determined by the way, this value is 0.7. This can be determined by PV over PG. From this equation, this PG is preset at the given temperature. So what is the temperature at number 1? 50 degrees Celsius. So 50 degrees Celsius. What is P set at 50? If you go to table A2 at 50 degrees Celsius, saturation pressure is going to be 0.1235 bar. So from this equation, we can evaluate PV. PV is going to be 0.08645 bar. And if you know PV, then you can substitute this PV into this equation right here and right here. What about P1? P1 is given here, 0.9. So this P1 is 0.9 bar. Then we have everything. We can determine omega 1. Omega 1 from this at the inlet is going to be where is Omega 1? Oh, I don't have it. I need to calculate that. Calculator 0.08645 divided by 0.9 plus 0.08645 multiply by 0.622. We have 0.0545. So this one is 0.0545. So this is the humidity ratio. This humidity ratio is mass of water vapor divided by mass of dry air. Now, if you consider conservation of energy principle between number 1 and number 2, mass at the inlet should be the same as mass at the exit. We can use this equation for air. We can also use this equation for water vapor, assuming that there is no chemical reaction between air and water. So we can use this equation for air first. Ma1 is the same as Ma2. We can use this equation for water vapor. Mv1 is Mv2. So from this, we can say this Mv1 over Ma1 is going to be the same as Mv2 over Ma2, which is omega 2. So from this, we learned that omega 1 is the same as omega 2, which is 0.0545. And how can we determine omega? Omega 2 can be determined by 0.622 times PV2 over P2 minus PV2. And this one is 0.0545. And we know P2, 1.5 bar. Then we have everything but PV2. So we can evaluate PV2. So from this equation, PV2 is 0.1441 bar. If you know PV2, then we can evaluate relative humidity, which is phi2. Phi2 is PV2 over PG2. By the way, this PG2 can be evaluated by P set at the given temperature. What is the temperature? 195. So this is 195 degrees Celsius. And this PV2 is available right here. And P set at 195 is shown here. 12 point, oops, it's not 12.54. We don't have 195. So we can do a linear interpolation between these two numbers. So that is right in the middle between these two numbers. Let's take the average of this. 14.04. So P set at 195 is going to be 14.04 bar, and we have PV2. So we can evaluate phi2, which is 0.01026, which is approximately 1%. That's how you can evaluate the relative humidity. As you can see, initially at the inlet, the relative humidity is 70%, which means that your water amount in the air is 70% close to the maximum amount of water that can be, in the air at the temperature. However, for the same mass of dry air and for the same mass of water vapor, just by increasing temperature from 50 to 195, the same amount of water, the relative humidity drops to 1% from 70%, because when you increase the temperature, you can, the air can contains more moisture because the saturation pressure Pg goes up from 0.12 to 14.04. So it can contain much more amount of water vapor when you have higher saturation temperature. That's why in winter, when you run the heater for a long time, the relative humidity of your house drops significantly because the saturation pressure of the air at the given temperature after heater is on, they increase dramatically. Therefore, the relative humidity goes down. Okay, that's why we use a humidifier in winter. So that's everything about the studying the relative humidity and humidity ratio in this energy balance equation. So let's go to the second problem. The second problem is that the power input for this compressor. So how can we determine power input? We can use energy balance equation. So what is the energy balance equation for a compressor? A compressor has one inlet, number one exit, number two, and we have power input to this compressor. So if you want to evaluate the power input for this compressor, which is this one, we can use energy balance equation. So let's write the energy balance equation for this compressor. If you're not sure what is the energy balance equation for a compressor, you can start with the general energy balance equation, which is Q in plus W in plus m dot at the inlet. This one has enthalpy, kinetic energy, and potential energy, which is the same as heat transfer out of the system plus energy transfer from the system plus mass transfer at the exit number 2. This has enthalpy, kinetic energy, and potential energy. So from this energy balance equation, we assume that there is no kinetic energy change, potential energy change, and it is well insulated. That means that there is no Q. So we can neglect Q in, Q out, and compressor consumes power, does not produce power. We only have one inlet, one exit. So m dot at the inlet is the same as m dot at the exit. So you can just say m dot. So I can remove this subscript. Then the equation is going to be this term, and this term. So what do we have? W dot in, which is what we want to calculate, is going to be a plus m dot H1 is m dot H2. So this is the energy balance equation we used in Thermodynamics 1. In Thermodynamics 2, we don't have just dry air. We have a mixture of air and water vapor. So instead of m dot H1, we can use this equation. Because m dot H1 is H1 dot, which is m dot of A times HA plus omega HV. So let's rewrite this equation in this form. W dot in plus m dot of A at number 1, at the inlet number 1, this has enthalpy H, specific enthalpy A, HA number 1 plus omega humidity ratio at the inlet times HV at number 1 is going to be this one, M dot A2 HA2 plus omega 2 HV2. Again, we use this equation in thermo 1, assuming that we only have a pure system, just air. However, in thermo 2, we solve it more specific. Instead of air, in reality, it is air plus water vapor. So instead of m dot h1, we don't use that simple form. We use m dot a times ha. This is for air, and m dot a omega 1 times hv. This is for water vapor. So we have more complicated enthalpy term to represent air and water vapor, both of them, rather than just the air as the thermal 1. Okay. So let's solve this equation one by one. First of all, this is the unknown. What about m dot a? We do not know m dot a. So let's find m dot a. So how can we find m dot a? We can use the volumetric flow rate. So how can we use volumetric flow rate to calculate m dot a? Are we going to use this equation, which is m dot is density times volume flow rate? We can use this equation if we have air only or water only. However, now we have a mixture. We want to determine not just m dot, but m dot of dry air. So we are not going to use this form. Instead, we can use the ideal gas equation of a state for air. Ideal gas equation is going to be PV mRT. We can apply this ideal gas equation for air only or water vapor. So let's do air only because we want to determine M of A. So if we use M of the air only ideal gas equation, this equation is going to be PA V MA RA times T. We do not say VA or TA because our assumption is each gas, each component of the mixture occupies the entire volume, and each gas, each component to share the same temperature. So we only, distinguish pressure, mass, and gas constant when we use the ideal gas equation, okay? By the way, we know the volumetric flow rate, which is V dot. It is 0.8 cubic meters per second. So where's the V dot? We don't have it. However, we have a V. So then you can divide each term by time t. Then V over time is going to be V dot. M over time is going to be M dot. By the way, there's a PA in front. There's a M, it's not just M, it is MA. So instead of M dot, it's going to be M dot of A. We have RA, we have a T. So using this equation, we can calculate M dot A. This V dot is going to be 0.8 meter cube per second. What about PA? we only have the pressure at the inlet, 0.9. That is not PA. That is just P. 1 is going to be 0.9 bar. This P1 is going to be PA1 plus PV1. By the way, we already calculated PV1 in the previous process. In the previous example, part A, we already calculated PV1, which is this one, 0.08645. So this one is 0.08645 bar. Then 0.9 is this one plus PA1. So we can, calculate PA1. If you do, I don't have the value. You can calculate that. 0.81355 bar. So this one goes here. What about R of A? R of A can be determined by universal gas constant divided by molecular weight of dry air. Universal gas constant is always 8.314. The molecular weight of dry air is going to be not here. Molecular weight M of air 28.97. 28.97. What is the temperature? 50 degrees Celsius. So I'm going to say 50 degrees Celsius. Then it is incorrect. You have to use Kelvin. So instead of 50, we can use 323 Kelvin. Then we have everything. You can determine m dot of A. If you do, m dot of A is 0.702. M dot of A is 0.702 kilogram per second. So this one goes in here. Let me write on top. 0.702. What about this one? 0.702. What about HA1? We do not know HA1. However, we can calculate this HA1, or we can go to table, ideal gas table for air. Ideal gas properties of air. There's a H. So this HA is the specific enthalpy of dry air. So we can use air property, which is right here. So what is the temperature at the inlet? The inlet temperature is 50 degrees Celsius. So what is 50 degrees Celsius in Kelvin? 323 Kelvin. So we should evaluate H value at 323 Kelvin by using linear interpolation between these two numbers. What about at the exit? 195. Instead of 195, what is the temperature we have to use? Plus 273, 468 Kelvin. So where is 468 between these two numbers? 468 Kelvin. So we are going to do a linear interpolation between these two numbers to evaluate H value. So let me do that. H at 323 Kelvin is going to be, I already did, 323.3 H at 468 Kelvin is going to be 470.2. By the way, you can do a linear interpolation to evaluate these two numbers. Then we can substitute these two back to this equation here. This one is going to be 323.3. 323.3. What about this one? HA2 here, 470.2. 470.2. What about humidity ratio? Well, we already calculated humidity ratio. Humidity ratio is 0.0545, and we confirm that this humidity ratio does not change between inlet and the exit due to the conservation of mass principle. So we can use the same value, 0.0545. 0.0545. 0.0545. What about HV1, HV2? For moist air, HV can be evaluated as Hg. We can do that. Or we can also use another property table, which is table A23. So this is table A23 right here. And we have H value with temperatures. This one is in Kelvin. So what temperature do we need to evaluate? 323 Kelvin and 468 Kelvin. So we have to do linear interpolation between these two numbers. So let's do that. I already did. So let me give you the values. So H V. Oh, there's a bar on top of it. Let me explain this one later. H bar is going to be at 323. 323 Kelvin is going to be 110,740. HV bar at 468 Kelvin is going to be 15,707. What is the unit? Unit is kilojoule per kilomole. Wait, why it is kilojoule per kilomole? Because this value is on a molar basis. You can see bar on top of it. Then how can you convert this property on a molar basis to a property on a mass basis? Always use the same equation. N is M over M. So H bar, so this is molar basis, this is mass basis. This is mass basis. So H bar is going to be H over molecular weight. So that's how you convert. Again, when you see this bar on top of it, it means that it is on a molar basis. If you see there's no bar, that means on a mass basis. What H do we need? Mass basis. What H did we found? On a molar basis. So you need to convert this one into mass basis by using this equation. H over M. Oops. I made a mistake here. Forget about that. So you need to multiply this by kilomole per kilogram. So not this one, forget about that. And multiply by kilomole per kilogram. That's how you can get rid of kilomole, right? So it becomes kilojoule per kilogram. So what is the, the property that has kilomole per kilogram? The molecular weight has a unit kilogram per kilomole, which is the inverse of this one. So you have to divide this value by molecular weight. Then you get H. Okay. So what is the molecular weight of water vapor? Molecular weight of water vapor is 18.02. So this HV1 is going to be H bar V1, which is this one. This is H bar V2. So this one divided by molecular weight. This is H bar V2 divided by molecular weight. So what is this value? 10,740 divided by molecular weight. 18.02. 18.02. What about this? 15,707 divided by 18.02. So forget about this part. Divided by molecular weight. Then now we have everything. You can evaluate the power consumption by the compressor. And if you calculate that, it is going to be 115.9 kilowatt. Not easy, right? So if I give this problem in your first exam, can you solve it? Of course, this problem takes a long time because there are, the many properties that we need to evaluate. So in your first exam, I will provide only the tables that you need so you can save some time. Rather than giving you the entire table, I may give you this small table that you can find the molecular weight directly for water and air rather than find this value from the entire table. So I will do my best to minimize the time. However, you need to, practice these problems as many times as you can so that you can understand how you convert between two different, the approaches between mass basis on a molar basis. And also you need to be able to convert this energy balance equation that we used in thermo 1 to this energy balance equation that is in thermo 2. Okay, so this is the key part. You need to be able to write this equation. If you made a mistake evaluating one of the properties, then you may get the small deduction, so that's not going to be a problem. However, if you cannot get this governing equation in thermo 2 for the mixture, then it is a problem. Okay. But that's not the end. We want to evaluate the rate of entropy production. So this one problem takes an hour, okay? So let's look at the last problem. So if you want to evaluate the rate of entropy production, that means that you need to be able to evaluate, you need to be able to determine the entropy balance equation. What is the entropy balance equation? If you don't remember, let me give you the, the general equation. So this is compressor system, open, steady state, compressor system. So the energy balance equation is going to be entropy goes in minus entropy comes out plus entropy that is generated by the system should be the same as the change of entropy of the system. So this is the entropy balance equation in general. First, it's a steady state system. So there is no change of entropy of the system in time. Always, when you have this kind of balance equation, the right-hand side is always time-dependent term. This is a space. So what happens at the inlet, what happens at the exit, what is created is going to be what happened to the system in time, before and after. So how can we evaluate entropy transfer in? There is no entropy transfer by work. So it's going to be either entropy transfer by heat, which is Q in divided by temperature, or entropy transfer by mass, M in times S in. So it's going to be either this one or this one. But in the exam, and in the problem, it says it is well insulated. That means that there is no heat transfer. So you can neglect the entropy transfer by heat. So the only entropy transfer is going to be by mass. So here is the schematic of our system. We have an inlet number 1. So there is an entropy transfer at the inlet number 1, M1 times S1 minus exit number 2, M2 S2 plus Sgen is going to be 0. By the way, Sgen is entropy generation. We want to determine the rate of entropy generation. How do you determine the rate? Divide each term by time. By the way, we only have one inlet, one exit. So inlet mass at the inlet is the same as mass at the exit. The M over T is M dot. S over T is going to be S dot. If you move this one to the right-hand side, this one to the right-hand side, this equation becomes S dot gen is going to be M dot S2 minus S1. So this is the equation we need to solve to determine the rate of entropy generation. Then how can we determine the rate of entropy generation? We can use the same equation for the mixture property. How do we evaluate S1, S2? By using this equation. S is going to be MA SA plus omega SV. This one first. MA2, 2 SA2 plus omega 2 SV2 minus this one. MA1 SA1 plus omega 1 SV1. So this is the equation that we need to solve. Previously, I told you that the mass at the inlet, where is it? Trying to find my solution here. Down here. Okay. Previously, I told you that, due to the conservation of mass principle, MA1 is the same as MA2. MV1 is the same as MV2, right? MA2 is the same as MA1. So I'm going to remove this subscript. What about omega 2, omega 1? Previously, we confirmed that omega 1 is the same as omega 2 due to the conservation of mass principle. So omega 1 is the same as omega 2. We know this value, which is 0.0545. What about M dot A? 0.702. So this one is 0.702. This one is 0.702. This one is 0.0545. This one is 0.0545. So if I rewrite this equation, it is 0.702 kilogram per second times SA2 minus SA1 plus omega, which is 0.0545 times SV2 minus SV1. Then how can we evaluate SA1, SA2 minus SA1? We can use the entropy change that we studied in chapter 6. If you don't remember chapter 6 of EGR456, let me give you the the equation. S2 minus S1 is S degree 2 minus S degree 1 minus gas constant R times natural log P2 over P1. Okay, so we can use this equation. So let me use this equation for dry air. Let me use this equation for water vapor. So this equation becomes 0.702 kilogram per second times S degree 2 minus S degree 1 minus gas constant R. This gas constant R can be evaluated by R bar divided by molecular weight. By the way, this is for air. So MA times natural log P2 over P1. This is going to be PA2 over PA1 because this is for air. SA. Then the second term plus 0.0545. Now we have S degree V2 minus S degree V1 minus gas constant R divided by molecular weight of water vapor, natural log PV2 over PV1. So if you solve this equation, we can determine the rate of entropy generation. So how can we determine S degree for dry air? If you go back to this problem statement, oh, there's a S degree for dry air. There's a S degree bar for water vapor. So we can use this equation and use this table to evaluate S degree for dry air. We can use this table to evaluate S degree for water vapor. By the way, gas constant R is going to be 8.314. Molecular weight of dry air is available right here, 28.97. This one is 8.314. Molecular weight of water vapor is this number of 18.02. And we just need to find each property value. By the way, since it is already time, so I will finish here and then continue this equation next Tuesday. Okay? Any question? No? All right. See you next week. I can tell you that this course is very time consuming, and you need to spend a lot of time to solve these problems. Otherwise, you cannot do everything the day before the exam or the week before the exam. You need to keep solving these problems. Okay? All right. See you next week.